let's get started. Okay, my name is Anil Yadav and I am here for the tutorial 4 on fundamentals of micro and nanofabrication. So I have taken most of the slides from Professor Sushoban Awasthi's course from ISC Bangalore. So today we will start with the last time we have discussed with some diffusion and
Anil, sorry to interrupt.
yes, yes.
But I don't know if you have to record it and put it on the portal. I don't know.
No, I will record it and put it in the portal.
Okay.
So-
Is it recording now?
Yeah,
For
it
other
is.
students, I'm saying.
Yes.
For other students, I'm saying. Is it recording now?
Yeah, it is recording only.
Okay, no problem.
Okay. Yes. So if you have any doubts from the previous class, you can ask, or otherwise we will get started for the next session.
Yes. Okay. Fine.
Okay. So today we will see the defects in the native oxide films that we have grown in the previous session, which are through the oxidation process, wet and dry oxidation process. So today we will see what kind of defects are there in the native oxide films that originate while we are doing the oxidation. Okay. So let us see. Say there are mainly four types of defect that comes when we do the oxidation, whether it is dry oxidation or the wet oxidation. So in this so there are these kind of defects. Some is like at the interface due to dangling silicon bonds. This is SiO2 interface. Okay, so at which are inside the silicon, not in the SiO2 but inside the silicon, not in the oxide layer. So at the interface, because of the dangling bonds, because of the unsatisfied silicon bonding, so because of that these kind of defects originate. And another one is SiOx, because of the these defects are near to the interface but these are inside the SiO2. This is because of the stoichiometric configuration is not proper, as it is not SiO2 but it is SiOx. Maybe that X may vary in between 0 to 2. Okay, so this is because of that. And another type of defects which are inside the SiO2 film, which are due to the ionic impurities, which like small atoms which are sodium or potassium kind of due to the sodium or potassium contamination, because these moves very fast inside the SiO2. Their solid solubility is too high, and because of these there is a kind of dielectric breakdown happens. Yes, dielectric breakdown happens at very lower voltage if these kind of defects are higher. And another kind of defects are deep in SiO2, so which because of IO bond breaking. So the we call it oxide trap charges, fixed trap charges we can no not fixed, right, oxide trap charges we can say, because of the breaking in bond of SiO2 we can also say. And this SiO2 is not crystalline but this is amorphous. Okay, so there is no kind of regular arrangement of SiO bond atoms. So in this one, because of the breaking of the silicon and oxygen bond, this may happen. They create a defects which are oxide traps. Okay, so now we will see the fixed trap charges, which are because of the stoichiometry problem, which is at the very interface of SiO2, and like one or two mono layers kind of the of SiO2 are because of the stoichiometry. So these SiOx, they trap the charges. They will trap, definitely they will trap, and we can minimize it, but they will be there because of the lattice mismatch or surface energy kind of problems. They will be there. And why this happens is because of improper oxygen oxygen is not reaching properly over there, so that is why. And because this layer, okay, if you okay, here I will show. So this is SiO2 at the, this is Si interface, and this is SiOx. This particular layer is SiOx, and this SiO2 for for oxide growth, oxygen has to diffuse through this SiO2 inside. So this is the layer SiO2 interface, which is exposed to the outer environment. There is oxygen, and this oxygen will diffuse to the Si interface at this SiO2 interface, and there it will react with silicon and form the SiO2 at this position. So at this position it will form SiO2, but because of the Si concentration difference at this position, silicon here at this right side, silicon is, there is silicon will diffuse towards the SiO2 because of the concentration gradient. Okay, so this concentration, can you see this concentration is excess Si concentration, and this is the excess oxygen concentration in SiO2. At this position there is kind of some deficiency of oxygen at this point, but because of the silicon has diffused from Si to SiO2, so that is why it forms there is less oxygen, and SiOx is formation is there at the interface. Okay, so and which causes the fixed oxide charges. Now how can we reduce the fixed oxide charges? So like there is kind of deal triangle, we will come into that, onto that. So we can do after the oxidation, either with whatever it is, wet oxidation or dry oxidation. After that, if we anneal that our substrate, our silicon wafer in nitrogen environment at whatever temperature, so it will, nitrogen or argon, which is like inert atmosphere, if we anneal that, it will reduce the defect density. Okay, can you see this is at lower temperatures, when we have annealed our substrate at in oxygen environment or outer environment, so the defect density is around more than 6 into 10 raised to power 11, which is at this temperature you can see, which is around 850 or something. If we anneal our substrate after the oxidation, or in whatever we have done the oxidation at higher temperatures, that is the case, or we have done at lower temperatures as well. So if we have done that, there will be fixed oxide charges will be there, because there will be a stoichiometry kind of defects will be there. So we can remove that by annealing that the substrate in any inert atmosphere. Okay, and this is reversible as well. Reversible in the sense is, if we again anneal the substrate in the outer environment or in the oxygen environment, it will whatever temperature we are keeping, accordingly it will generate the fixed oxide charges, fixed oxide defects. Okay, so it will be there. So after the oxidation, this is the oxidation, we have done the oxidation. Now at this point, after this point, we can remove the oxygen, we can create the inert environment inside the chamber itself, and we can keep it annealing for some more time, let's say 10 to 15 minutes. So that will remove these fixed oxide charges. Okay, these fixed oxide charges it will remove. So, and also this is a state process in the sense, it depends on the initial and the final conditions. At what condition finally we are removing the wafer from the chamber or from the furnace. So finally what we need to do is, we need to remove the wafer after annealing it in the inert atmosphere. Okay, let me see. And okay, and one more thing is this should be the final step. Otherwise what will happen is if you are doing another step at higher temperatures after this, because there won't be any inert environment, so what will happen is it will again create the defects, because it is a state process. It depends on the final state at what temperature you are removing and in what environment you are removing the wafer. Okay, so the final step should be this one, this higher temperature annealing in the inert atmosphere. If you are annealing again the substrate at higher temperature, it will create defects again. Okay, now so, and also these fixed charges are charges depend on the orientation of the wafer, so which wafer you are taking. So in one kind of orientation, these fixed charges are higher. Okay, the fixed charges are higher, and at 001 the wafer with the 001 orientation, these defects are lower, and that is why these wafers are used for the semiconductor, in the semiconductor industries, for the CMOS applications. Okay, in our mobiles or any kind of devices, these kind of wafers are used 100 or with 100 orientation. Okay, now the interface trap density, QIT, and which are the at the interface of SiO2, SiOX, which are inside the we can say inside the silicon. Okay, just inside the silicon. So what kind of these defects? Okay, that okay, interface trap charges, these are around 10 raised to power 10 per centimeter square, which are okay, and which originated due to the dangling bonds. Okay, how can we cure these dangling bonds? Just this is kind of a rearrangement of the silicon. So if we just anneal this at the higher temperature, and these dangling bonds can be removed, not can be removed, but can be minimized up to a certain extent. Okay, okay, where were we? Here. Okay, we just need to anneal these. Okay, and okay, these are and one more thing is how these the density of these defects is there inside a silicon, in between the band gap. So in between the band gap, this is the valency band, this is the conduction band. It is just a 90-degree rotation, if you can see, and we are showing the density of states because of these defects. So here is the conduction band is the nothing but the density of states in the conduction band and density of the states in the valence band. In ideal semiconductor, what should be, so in between this is the forbidden. Okay, so there should not be any energy states in between the conduction band and the valency band, but due to the defects there are some energy levels which are due to these kind of defects, interface traps. Okay, so how this is the density of the traps which is there inside at Fermi level. This is the intrinsic Fermi level. At the in the middle of the gap, these are minimum, but at the near to, as we go near to the interface or near to the conduction band or the valence band, it varies like this. Okay, it varies like this. This is experimentally proven, and what we can say from this one is, this is the thing I just wanted to tell. And and how can we reduce these trap density? Because of the this interface trap density, which is because of the dangling bonds. Sometimes it may rearrange, or what we can do is annealing in the forming gas. Forming gas is a mixture of hydrogen and nitrogen, which is 10% of hydrogen, or sometimes it is 5% of the hydrogen, and nitrogen is around 90% or 95%. Okay, because hydrogen is inflammable at top, which is whenever it comes 100% of hydrogen you cannot use, because as soon as it comes with the oxygen, it comes with near to the oxygen, it is pyrophoric, it catches fire. Okay, so with 10% of hydrogen we can do that, or 5% of hydrogen we can do that. Okay, so annealing for 10 to 15 minutes at 400 degrees Celsius, it can remove, because as we this hydrogen which is there in the environment while annealing, it will get diffused inside through the SiO2, because of very small size, the diffusion coefficient will be higher, so it will easily, so that is why it is taking very less time, only 10 to 15 minutes it can reduce the trap density in only. So as it will diffuse inside through the SiO2, so at the interface it will come in contact with the Si, which is unsatisfied, because of if Si is making four bonds, if there is one unsatisfied bond is there, as silicon is there, it hydrogen will go there and it will form SiH bond, so it will compensate it. It will satisfy the valency of silicon, so which will reduce this interface trap charges. Okay, and one more thing, if you anneal, this is the annealing in forming gas, this is the interface trap density, and it is this is the E minus EV, which is difference between the valency band and the energy. Okay, so this is we are going from valency band towards the conduction band. This is the kind of the defect density we can see through the band gap. And if initially it was here as deposited, so but as we have annealed for 10 minutes at 500 degrees C in forming gas environment, the defect density has reduced almost more than an order. Okay, almost about an order, more than an order. So, and after that, if we anneal it again in the nitrogen environment, what will happen is the defect density is increased. Okay, for 1 hour this is the defect density, and for 2 hours this is the kind of defect density. If we increase the time more and more, it will get kind of this thing. Okay, because at a higher temperature, it will break the bond of SiH, so it will be again creating the interface trap density. At higher temperature, it breaks the bond, and this hydrogen will leave from the interface. It may diffuse out of through the SiO2, or it may just go through, because of it can go through the interstitial sites, because of the very less size of the hydrogen, so it can go diffuse down into the silicon as well, or can diffuse out through the SiO2. Okay, now halogenic oxidation. So how this halogenic oxidation will remove these the defects which are created due to the mobile ionic charges, which are sodium or potassium kind of the ions which are there, because we cannot remove these kind of defects, or this kind of contamination, because it is everywhere. As soon as you touch the wafer, there is a metallic contamination will be there. So how you can minimize it, something which can react with these kind of ions and can stabilize it, which can increase the size of the molecule, and it should not move through. Okay, how it moves through the interstitial positions, but SiO2 is amorphous, so there are some gaps through that it can move easily. Okay, so how can we do that? If we add some chlorine kind of gas through some sources, so this Cl2 or HCl gas, if we just keep it and anneal it in this kind of environment, so this HCl or chlorine will diffuse inside the SiO2 and it will stabilize these ionic impurities. Okay, so there are some other things, because this chlorine sources HCl or some any kind of this trichloroethylene or trichloroethane, this is liquid, but these gases, just a minute, someone wants to join. Okay, so these gases are very toxic. Okay, so as soon as it come, you cannot inhale, because it will kill you definitely. And these kind of gases were used during the World War. So these are not these are very dangerous. So a proper care should be taken while doing these kind of things. Okay, so this is the thing now. So through the halogenic oxidation, so at higher temperatures, okay, this is the at the higher temperatures the defect density is okay, this is the defect density which is causing the breakdown at lower temperatures. Okay, this is the defect density causing this I need to check once. Okay, this defect density. So at higher temperatures, this is showing that it is the okay. What I want to tell you is there are sodium ions and potassium ions. Because of these ionic mobilities through in the SiO2, so if we are using it for a dielectric purposes, like say in a MOSFETs or something, there is a term which is dielectric breakdown. Dielectric breakdown happens when the current suddenly increases, the gate leakage current which suddenly increases. So at that moment the device is damaged. So we cannot that device is damaged and we do not want that. Okay, so in this case, if and that happens because of these kind of impurities which are ionic impurities. And so how we can reduce it? By annealing that in halogenic by doing the halogenic oxidation. Okay, so at lower temperatures, if we are doing that, that is a much better choice of lower temperatures are a much better choice. But if we are doing at higher temperatures, the stacking fault, which is due to the alignment of the layers, which is due to the what to say. So okay, this is kind of the alignment of Si, and there is another alignment of SiO2 which is there. So these atoms are connected like this. Okay, so and okay, in this one these atoms are connected like this only. So but these are stacked, well stacked, but the next layer, as the next layer comes, how if these atoms connected like this, there is a kind of this stacking fault. Okay, this in between these two layers. So it when we do the halogenic oxidation, it cures the when we do the this in dry O2 and HCl, so it cures these stacking faults, these stacking faults at higher temperatures. But at the same time, it is doing the causing the breakdown voltage is causing. Okay, so defect density is increasing at this point. So there is some kind of we need to take care. So at what temperature we need to do that thing. Okay. So and now how can we so okay, you have done the oxidation of dry oxidation or wet oxidation of your 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 silicon wafer, so how will you characterize that the thin film? So how will you, first thing you need to check is the thickness. So you just want to check the thickness and the quality of the film. How can you do that? The best and very less time consuming thing is the ellipsometry. It you can do thickness measurement using ellipsometry in just within 1 or 2 minutes. And another thing is the profilometry. You can check the thickness with using the profilometry. In profilometry, what happens is there is a kind of needle and there is kind of tip. So if this is your silicon wafer and you have grown the silicon dioxide, for that you need to do it, there should be some kind of step should be there. So this tip will touch at this touch the surface, and as this tip will move or the substrate will move, so there will be a step height. So this by this method, this is kind of a mechanical method. By this method you can check the step height and you can check this oxide thickness. And this is an optical method. Ellipsometry is an optical method. So this is SI, this is SiO2, okay, SiO2, and the light will pass, light will go and it will reflect back, and with the polarization effect, it will give you, the ellipsometry will give you the thickness, and also it will give you the what to say, refractive index. Okay, refractive index, N and K, it will give you the refractive index. From the refractive index you can see the quality of the film. More will be the refractive index density, higher will be the density of your SiO2, and better will be the film quality. Okay, through this method, ellipsometry is kind of a very powerful method. You can within minutes you can check the refractive index and the thickness at the same time, and it is non like damaging. It doesn't damage your substrate as well, other methods. And this is X-ray reflection. This also gives you the thickness and density just by the reflection of the X-rays from these two different layers. Okay, and that same this ellipsometry does. And with SEM and TEM you can check the morphology of the film of the top surface, and also the thickness. Thickness is, how can you check the thickness? If you have a full wafer, okay, yeah, this is Si, this is SiO2, but just break this wafer from the middle, and you can take the cross section in the SEM or TEM, so you can check the this thickness. Okay, in AFM also you can do two things. Roughness also you can see, and surface topography, morphology also you can see with the because this is kind of a mechanical process. It also uses a tip. This can be in contact mode or non-contact mode, and with the potential, it measures a kind of potential at the surface, and it gives you the morphology of the film, and also gives the roughness as well. And also you can check the thickness as well from the AFM if you can make this kind of step. Okay, it gives you roughness. That is the same thing. It will the tip will move and it will give you a step height. So with AFM as well you can check the thickness. Okay, so now next we will see the chemical vapor deposition. And this is the another additive process which adds the layer of the another material or the same material, we can say a silicon on silicon, dioxide on silicon, or any other materials can be epitaxially grown over a substrate through chemical means. This is the CVD, abbreviation of CVD, chemical vapor deposition. There
Anil,
yes.
Anil, one doubt I had.
Yes.
Earlier, in the characterization techniques of thin films,
Yes.
AFM, like ellipsometry and profilometry, we can do immediately, right? We will get immediate results of
Yes,
thickness.
in profilometer and ellipsometer you can get immediate results.
Okay.
Huh.
AFM, I did not understand. What is AFM?
Okay, in AFM there is a this kind of okay, just give me a minute.
Yes, yes, sir.
Huh. So you have a substrate. Okay, there is some kind of morphology over that. There are kind of film. Okay, so there is a tip. Okay, which is vibrating. Okay, this tip is vibrating up and down. There is a frequency, certain frequency of the tip. Okay, so it will go
Mm-hmm.
up and down and will be moving this direction or this direction.
Okay.
Okay, so with the frequency, the change in frequency or the how it is behaving along accordingly, there is over the tip there is some optical kind of light is there, and that goes to the detector. Okay, here on the other side with the how much it is moving up and down, that will depend on the morphology of this sample. Okay.
Okay. Okay.
Huh.
Sure. Sure.
Okay, so that will depend, and it will give this detector will have a kind of pixels. Okay, so how this is moving, that will give you a like I'm not going into that much detail. Okay, so but it will give you kind of a morphology that according to the movement of this tip.
Okay. Okay.
Okay.
I got an idea of how it works. Thank you.
Yes, yes. Okay, so it is a bit different from the profilometer. Okay, it is a bit different. But in this one, profilometer I haven't done. But I actually I just know about this. It is kind of a mechanical process. It also uses a tip, but that much in detail I don't know about the profilometer. But I know about the AFM, that this is the thing happening in the AFM. Okay.
Okay. Okay. Thank
Any
you.
other
Thank you
detail
very much.
you need?
No, no. Thank you. Thank you,
Okay.
Anil.
Okay. Yeah. So in chemical vapor deposition, we uses some kind of precursors. Okay. So what we are going to deposit, like is silicon on silicon epitaxial growth you can do, or any kind of other thin film growth you can do. Okay. So there are two kind of depositions which are chemical. One is chemical vapor deposition and another is physical vapor deposition. In chemical vapor deposition is these in chemical we are using some kind of gaseous precursors, or we can say precursor. We use precursor which is flown through a chamber. This is chamber. This precursor is flown through the chamber, and it reacts with the substrate. Okay, it reacts with the substrate. There will be some products. They will be going out at the same time, because there is a continuous flow of the precursor along with the nitrogen or some carrier gas. Okay, so this is a chemical by the chemical means we can do. So we will go into the detail in the subsequent slides. So in metal organic CVD you can grow some kind of organic materials, organic thin films that we are not going to cover in this lecture series. And there is vapor phase epitaxy and atomic layer deposition. These atomic layer deposition and CVD will cover. Okay, and in this one there is a very good quality of material is there, so which can be used for kind of dielectric applications. And this is a costly and complex, because we are the precursor that we use for CVD. So these are kind of volatile, pyrophoric, and the byproducts are kind of HCl or something which should be treated before leaving to the environment. Okay, they can cause they are hazardous to the environment as well as our health. Okay, So so these kind of coatings are used in the semiconductor industries for some dielectrics or for packaging kind of things. You can use silicon, germanium, or these compound semiconductors also you can grow. Silicon nitride, SiO2. Mostly SiO2 is used for the passivation, is grown by the CVD. Okay, and another is the physical vapor deposition. In physical, okay, in chemical vapor deposition, there is kind of like if you want to grow like gallium arsenide or silicon nitride or silicon oxide, so in these cases these are compounds. So you need two precursor. One will supply the gallium, another will supply the arcesium. Okay, and one in the silicon nitride, one will supply silicon, another will supply the nitrogen. So two precursors you will need. But in physical vapor deposition, you simply heat it up, or you simply do the plasma of that on that. So, or there are several methods that we will come upon. Okay, evaporation, directly evaporation you can do. Sputtering is nothing but like by means of the plasma creation, you just take out the material from the from your target, and that will get deposited over your substrate. Okay, so this if you have SiO2, you want to deposit SiO2 or silicon nitride, you need to have a target of SiO2, or like say if you want to Al2O3. These kind of oxides or silicon nitride. So these kind of oxides, nitrides can be directly deposited over the substrate using this PVD. Only one target is required. Only this SiO2 target is required, Al2O3 target is required, but there will be a poor quality. Okay, this is very easy to grow. A poor material quality in the sense, because it may damage the SiO2 bond. Okay, and there will be a stoichiometry, though not that much of good stoichiometry will be there. Okay, and another thing is cheaper and easier, because you just want to heat by means of e-beam kind of. If you put the e-beam evaporation selectively, you can with the electron beams. Okay, if you have a bot kind of thing and there is material which is SiO2 or Al2O3, there will be an electron beam source. This electron beam we can make it fall on these electron beams. We can make it fall selectively over the SiO2, and that will heat at this position. It will take at the very high temperatures, and it will evaporate SiO2 from here, and that will get deposited. These kind of things are done at very low temperatures, no, at very low pressures, kind 10 raised to power 6 minus 6 of millibar, kind of 10 raised to power minus 5, 10 raised to power minus 6 millibars. Okay, so this happens, and these can be used. This is mainly used for metals, actually, to deposit the metals. This physical vapor deposition is used mainly like if you want to deposit aluminum, gold, platinum kind of things. Okay, and sometimes dielectric for the passivation. For passivation we require kind of thicker dielectric layers. Okay, for passivation, and so at that time you can use these kind of methods, because this takes less time. Directly evaporation, it takes less time, but in those kind of passivation, this stoichiometry is not that much issue, so we can use this physical vapor deposition kind of techniques. Okay, before going into the CVD, we need to I will tell you about some terminologies. What do we need for a better kind of film depositions? Okay, there are some terminologies like uniformity. Uniformity is the thickness variation of the film. Okay, so like this is your silicon wafer or any kind of substrate, let's say any kind of substrate, and you are depositing any film over that. I am just assuming this is silicon and you are depositing silicon dioxide or aluminum oxide, Al2O3 or SiO2. Let us say SiO2 you are depositing. So this is the thickness of the film SiO2. If this SiO2 is not uniform in the sense the thickness over here at this position is T, and at this position it is something T1, okay, which is there is a thickness variation over the substrate. So this is the non-uniform kind of film. Okay, we need the thickness which is the same whole over the wafer. This SiO2 thickness should be same, otherwise in subsequent processes it will be it won't be good for the device fabrication. That this lithography, this is kind of a lithography, whatever we will use the post processing, maybe lithography or and some other kind of purpose. So in lithography what will happen, this thickness is less, this is T and this is T plus T1, okay, this is T1, this is T2. T2 is greater than T1. Okay, at this position T2 is thickness is higher. So when after your lithography, when you do the etching of SiO2, when you do the SiO2 etching, so what will happen, this is kind of a dry etching process. So it will etch this thickness was kind of just let's assume we wanted a opening of W thickness, W width, we wanted a W width. If the thickness is lower, you will get W plus delta W because it will over etch. Okay, this wafer is the after etching you will find the wafer quickly. Okay, it will be exposed to the environment quickly, so it will etch through from this side, okay, as well. So in this one you will get a feature size more than the expected one, and in this with the higher thickness at this point what you will get is it won't even get etched till that position, because it will require more time, and if we give this one more time it will get over etch more. Okay, W plus delta W plus delta W whatever it is, so it will take more and more, it will get over etched more, and your feature size will be compromised in this position. And in this case when it is not etched, we wanted it to be etched but it is not. So in this case this device won't work at this position, the device won't work, and which is critical because there are billions of transistors or transistors in a chip. So if the connection, if there is some connection error in that, so everything is gone, okay, because of this non-uniformity. So this should be taken care. And now the conformal coverage. So in conformal coverage, so you have this silicon and you have SiO2, this kind of you have already. So now you want to deposit a metal over that over SiO2. This is a step coverage kind of thing. So if this metal is covering everything, like it is following the same step, same morphology which is underneath, then this is a conformal coating. Okay, but in reality what happens is at the edge, at the sharp corners, this is kind of like this. Okay, it is not deposited properly, but it is kind of a round shape will be there, so which is poor conformal coverage. Okay, so the next step, if you are etching something, so it will get etched faster than that. So there or if this is non-conform, if poor conformal is there, if it is not coating at all at this position. Okay, what I will see, if it is not coated at this position, so this connection will get broken. Okay, this connection will get broken and there won't be any continuous flow of the charges. That will also be also kill your device. Okay, so the step coverage is nothing but this is same as kind of the conformal thing. Okay. Now for CVD you need to know a bit of the fluid dynamics. So how the fluid flows inside a reactor, or how generally how fluid flows, because we will be using some precursors which are in gaseous form. Okay, so for that you need to how the gas or fluid flows through a pipe or through a chamber. Okay, so in this one let me okay, so there are some things. One is the molecular flow. Molecular flow is there when there is very very low pressure. These atoms, let us say these are the atoms of the gas, they are not feeling any kind of like is no kind of collision with the, they don't even see if there is another atom or atom in the chamber. Okay, if the chamber is at a very low pressure, then this kind of molecular flow is there. Okay, so in this one the particles are just going in the random direction because they are not colliding, they are not seeing any kind of force on them. And in laminar flow there is a like collision of the particles, and at not very high pressure, not at very low pressure, so there is in between which flow in a uniformly in a straight direction. So this is the laminar flow. And in turbulent flow, if we increases the pressure, okay, these particles, these atoms will collide with each other so much that there will be a kind of random that you can see if there is a pipe, when you press it from the the front, there will be kind of this kind of flow you can see. And when there is pipe, when pressure is not that low and not also not that high, in your, when you wash your car or bike, you can see that thing. If the pressure is normal, so there is kind of you can see through the water. This is kind of that laminar flow. When you press from the front, there is a kind of random because of the higher pressure. So in that case there is a turbulent flow. Okay, and this kind of molecular flow is there when in physical vapor deposition, or when there is very low pressure is there inside inside CVD, or not in the CVD but in the PVD physical vapor deposition. We need a very very low pressure so that there is no collision with the other atmospheric oxygen or nitrogen, whatever, so that whatever material that we want to deposit, that directly can go and sit over the substrate. Okay, so which things actually decide the regime? So this is the viscous flow and this is the molecular flow at very low pressure. So one is the pressure that decides the in which regime the fluid is flowing. Okay, and another thing is the diameter of the tube. Okay, if more is the diameter, that more will be the molecular flow kind of there. Okay, tube diameter lesser, or okay. And another thing is the flow rate. At flow rate is nothing but the pressure only, which is the kind of more flow rate will be more when there will be more pressure. And viscosity of the material and density of the material, so these things decide whether the flow will be viscous or the molecular flow. So what are the parameters? There is Knudsen number and Reynolds number. That this Reynolds number we will be looking whether this flow is laminar or this turbulent flow. That we need this is the typical Reynolds number that should be for the laminar flow. So typical CVD reactors not typical, most of the CVD reactors work with the laminar flow regime. Okay. So what is the Reynolds number that we will see? So this is the formula for the Reynolds number. We are not going to derive because this is not a this is out of scope of this this course, because we do not require that much, because we are reading the CVD and we do not require this much of information. We just need to know whether this is a streamline flow or like turbulent flow. Okay. So it depends on the radius of the tube and average flow of the like we can say the velocity of the atoms or the molecules and of the gas, and the density of the gas and viscosity of the gas. Okay. So for laminar flow, this Reynolds number should be less than 1000. Okay. And in our typical this CVD reactor, it is around in between 1 to 100. So these things you should know at okay, this what should be the Reynolds number for the typical kind of CVD reactors. Okay, it should be in the laminar flow regime. And in okay, so why it is required for the CVD this kind of laminar flow? Why the others regime cannot be used? In molecular flow, the pressure is very less. Pressure is very less. That is, not enough precursor will be there. Okay, to grow the material. Okay, not enough material, not enough that precursor will be there. So the growth rate will be very, very low in this case. And in turbulent flow, there will be the precursor is randomly coming and going, so there will be a non-uniformity will be more in this case, and which will be highly unpredictable, and there will be it should be repeatable also, right? It won't be repeatable in this turbulent flow, because you cannot control that. In laminar flow, you can control the things, how much thickness you want to deposit in, because there is a kind of streamline flow in that one. So so this is kind of a typical representation of a laminar flow. How does it how a fluid or gas or liquid flows through a pipe. This is the wall of the pipe, and there is this is the velocity profile of the molecules or fluid inside a pipe. So in this position, at the center of the pipe, the velocity is higher. Okay, velocity is highest, and as we go from the center towards the walls, the velocity reduces, and at this position the velocity is 0, and at the walls, which is kind of a no slip condition. So we are assuming that there is a no slip condition. Okay, this is the formula for the viscous force at in this fluid, and force due to pressure from the higher pressure to the lower pressure, which is this one, which is given by this one, and in equilibrium the velocity is given by this formula. Velocity is given velocity Vr, which depends on the radius, on we can say radial position. Okay, this radial position velocity is given by this formula, and this mass flow, we can calculate the mass flow by just integrating over this area. Okay, this total mass, this is the total mass flow, and this is through a ring kind of with the dr thickness, dr kind of thickness of the ring. Through that, this is the dq mass of, this is the mass flow. Okay, the Poiseuille's equation law give you the mass flow. Okay, so and also you can relate with the electrical conductivity. We are not going into that. I am skipping that part because that is not required here. Okay, if you want to read that, you can watch the lectures there. So but it is not required, that that's why I skipped that part. And now we will go what is a CVD and what are the what are the things that are required in the CVD, what are the typical things. Just give me a minute. Okay, so this is a kind of typical representation of a CVD chamber, so which includes heating coils to provide the energy to the system. And there is a layer that we are depositing. There is a substrate that can hold the layer that we are going to deposit, that or maybe that can be silicon, glass, or any kind of substrate, silicon nitride as well. Okay, so this is a susceptor which is made of silicon nitride or kind of things, which can withstand up to higher temperatures. And also the contamination should be very less, so there should not be any metal inside this one. If you put the metal kind of, because as we have seen previously, there is a metal diffusion inside a silicon, and metal diffuses very fast inside the silicon. So this chamber should not, inside the chamber there should not be any metal. Okay, so everything should be kind of quartz or this kind of things should be there. This susceptor may be kind of because with quartz, which is SiO2, nothing but SiO2. Okay, these are so, and these are the chamber walls. So we to provide the energy, we can install the heating coils. Okay, to heat up the walls or just directly heating up the susceptor as well. Okay, we can do that. Anything. So, and another, there is a one thing which is the most important. There is a flow of precursor over that. Okay, the precursor is continuously flowing. There is a outgassing of this. There is a exhaust and there is inlet. In this direction, the precursor is flowing, and there is chemistry is happening at the interface. Okay, interface at this position, and because of that, there is a deposition of the material. So applications of CVD, just give me a minute. Okay, applications of CVD. So just growing epitaxial films. Epitaxial films are like, if you have a crystalline silicon, this is silicon, and over this is crystalline. Okay, this should be crystalline while for the epitaxial films. So if you are growing some silicon germanium, okay, or germanium films over that, germanium films. So So these films will be you can grow a more crystalline films over the silicon. That is the epitaxial growth. Okay, if over a crystalline substrate you are growing another crystalline material, that is the epitaxial growth. That can be homo also or hetero also. Homo in the sense you are growing silicon over silicon, you are growing silicon over you are growing germanium over silicon, which is hetero. Okay, which is you can say this is. And now and also that I also told in this case you will get a very high quality, good quality of the films. So these are for the device purposes. You can grow a CVD like a CVD. You can use CVD grown films for the devices like germanium, gallium nitride, or this kind of very. If you for device applications, if you are using, then you can use the CVD. Okay, so very good quality of films you can, but the thing is it is a bit expensive process, and because it is using some precursors that we will come in the next in subsequent slides. And now a deposition of high quality thin films. High quality in thin films need not to be like this crystalline. Okay, they can be polysilicon is conducting, which is for gate. Okay, for gate if you have Si over this, you have SiO2, and now you want to grow silicon. This polysilicon can be grown through CVD. Okay, this silicon CVD and which is conductive, which is because of the and which will give you the gate action. Okay, and metal films for the connecting in the sense is if there is a step, and this is silicon and this is SiO2 or any other material, and there is something else which you want to protect this silicon, and this is a step height. Okay, this is a step height, and over this if you want to grow if you want to deposit a metal, and this metal should be connected. Okay, in that case you will use CVD, because CVD is a kind of conformal growth will happen. Conformal, I just told you that this will follow the step of this one. Okay, so in that case you do not want any breaking of the metal at this position. You do not want a breakage. In that case you will use SiO2. You will use this CVD. Okay, otherwise your device won't work. High quality SiO2 films, silicon. Yes.
Sorry, Anil. Can you please repeat when the device will not work?
Okay. If you are using for the connections, okay, for this, you need a metal to be deposited, because over a silicon wafer, this is kind of a silicon wafer. Okay, just give me a new slide. Okay, over a silicon wafer, this is a silicon wafer. There are so many devices. One is here, one is here, one is here. So there are some steps in these. Okay, you want to connect this device with this device, or you want to get an outer connection over here. Okay, so you need to go through this. Okay, over this. So how? So there will be a kind of SiO2, and there will be some steps will be there. Okay, step heights will be, I am saying in this case this is silicon, and over this there will be steps. Okay, there will be steps. Okay, but you want to connect this one with this one. So how will you connect that? You will you need to do a conformal deposition. Okay, so that will be this there will be metal at this position, there will be a metal at this position. Okay, so which is connecting this or if you would have used any other deposition technique like PVD. So what PVD does is that we will come in the maybe next section tomorrow in the next tutorial. So what will happen is that will get deposited over here, over here, over here, but not on the sides. Okay, not on the sides in the sense what I am saying is at this position we won't get deposited. Okay, it will be deposited here, here and here. So there is a connection at this position. There is no connection in between this metal and this metal, so there is a breaking of the connection. Okay, so in that case you will CVD is more reliable. Okay, you will use the CVD in that case. Got it?
Understood.
Yeah.
Yes, sir. Got it. Conformal coatings.
Yeah, conformal coating is required. But in physical vapor deposition, it doesn't give that much of conformal coating. If there is a very deep trench in the sense, this is kind of a silicon wafer. Okay, this is a silicon wafer. Okay, and there is sometimes these kind of trenches are there, and you need to fill these trenches. Okay, that should be a conformal growth, but in physical vapor deposition you won't get that thing.
Correct.
Okay, so there will be a breaking of this connection at this point. So in that case you will use either ALD, atomic layer deposition, or chemical vapor deposition. In ALD you will read that is in atom by atom growth. So we will cover in the next section. That will be in the next class. Okay. So we will cover.
Okay.
Yeah.
Okay, Anil. Thank you. Yes.
Okay. So for every process there are some advantages and disadvantages as well. So advantages are because a wide range of materials you can grow, like SiO2, silicon nitride, germanium, and these kind of materials you can grow, because what you need is a precursor. Okay, so for that precursor, if you have available precursor for that material, you can grow that. And you will be given a temperature range, you will be given a for the temperature range and all these flow rate and all these things you need to optimize. So your seniors or before people who are working, they must have optimized for a wide range of materials, but what you need is, the main thing is the precursor that should be volatile. Okay, that we will come what type of precursor will work. If the precursor is available, a wide range of materials can be grown. So okay, and gaseous precursors are highly purified. Okay, gases you can purify up to a very good extent, but not the liquids you can purify. For if initially what we have seen is some solids and some liquids, how this wafer is fabricated from CG method or something. So there was a eutectic diagram that was there, and there is something if you will go and read about how this ethanol and alcohols are made, ethanol is purified. So in that case you will know that there is a certain extent beyond that you cannot purify that liquid, and that is done through the fractional distillation kind of processes. So in that case you will see that how much extent you can purify the liquids. So gases can be purified up to a higher extent. Okay. And see, this is a CVD has been used for a long years, and this is mature technology, and many people have optimized for various materials. Okay, so repeatability is good. Additional things are coming, some like low pressure CVD, plasma enhanced CVD, atmospheric pressure CVD. These kind of things are different kind of these reactive chambers are coming. Okay, and this deposition is strongly dependent on temperature. There is a certain range of temperature in which it is strongly dependent. Okay, So that we will see in the subsequent slides, where it is strongly dependent on the temperature and where it is weakly dependent on the temperature, and how we can tune with the different processes like low pressure CVD. You can tune that thing. Okay. And now a conformal deposition and a good step coverage you can see with the when they you can tune the temperature. Okay. And one of the best thing is it does not require very high temperature, high vacuum. Okay. To go at the higher vacuums, you require a very expensive pumps like scroll pump or diffusion pumps. There are ionic pumps. So these pumps are very highly expensive, and you do not require these kind of pumps, or because you do not require that much high vacuum, because atmospheric pressure CVD you can do. Okay. So, and there is disadvantage is high cost, because the precursors that you are using, they are dangerous and expensive. Dangerous in the sense, the precursors are pyrophoric. One is pyrophoric. They catches fire when they come in with the external environment. If they come in contact with the external environment, they will catch fire. And other thing, the byproducts that you are using, they are like they can release some sulfur gases or some chlorine gases. These should be treated. So for that you need scrubber. There is a scrubber unit that you need at the exhaust point. This scrubber unit will treat these gases before leaving to the outer environment. Okay, so this is highly expensive instruments are used to run this. Okay, so this is the thing. And okay, let me see. Okay, high temperatures are required. High temperatures, because there is something at in that temperature range only there is a reaction that happens at the surface. Okay, so this high temperatures are required. So if there the films get stressed, because if there is you are depositing silicon or silicon dioxide or silicon at the higher temperatures, the atoms are at far apart kind of while you are depositing. But when you come at the lower temperature, there will be a lattice, because of the lattice mismatch there will be a stress over the film. So you will find some cracks kind of cracks in the film, because of when you come from the higher temperature to the lower temperature. And another thing is you have very less control, because there are only two parameters that you can control for the film growth. Okay, one is the temperature, one is the pressure. In your instrument only these things you can control, but some new things are coming like atmospheric pressure CVD, low pressure CVD, but they also you can tune the pressure only, you can tune the temperature only. One is more plasma enhanced CVD. In that there is one more term that gets added, that is plasma. You can improve the film quality in that one. Okay. So there are very less, there is very less kind of control over the film. That is what I want to say. And for a CVD, what things that we need? Okay, what are the things that we need? Initial, that is the precursor. Okay, the precursor can be for if you are depositing any kind of material, silicon, there should be a silicon containing material should be there that can flow through this. Okay, that precursor should be I think that will come in the next slide. These are the 4 things that you required, 5 things that you required. One is the precursors, another is the substrate. That this substrate can withstand up to the higher temperatures. Okay, this limits the higher temperature, limits the usage of the wide range of the substrates. Okay, this goes up to 1000 to 1000, 1200, 1400 kind of degrees of the temperature. So glass, ITO, or plastic, these kind of substrates cannot be used inside this, because they cannot withstand up to that temperature. ITO cannot withstand above 400 degrees Celsius. This plastic cannot, plastic or PET sheets, that they cannot withstand above 150 or 140 degrees of the temperature. Okay, glass cannot withstand up to more than 600 or 700 degrees. Okay, but silicon, which is widely used in the semiconductor industry, this can withstand at higher temperatures. Germanium or silicon nitride, these kind of silicon dioxide, these can withstand. Okay, and this third one is the chamber wall. This should be this chamber wall should be non-contaminating. Non-contaminating, it should not be of metallic. Okay, if it is, there is a metallic, that metal will get out of from the wall, it will get diffused inside your substrate, that will damage your devices. Okay, and this chamber is generally of like quartz. Okay, maybe this quartz, and there is susceptor. Susceptor is over which you keep your substrate. Okay, or which you can keep your substrate, which is typically of quartz, and it should be inert and non-contaminating as well. And one is the final one is the heater, to provide the energy for the reaction to happen. Okay, this can be thermal in IR or RF kind of inducting coils that you can wrap over this, so which can heat the walls, or either the walls or directly to the susceptor or to the substrate, that can directly heat. So because the growth, or not the growth, the deposition is happening over the substrate. What we need is, we need this thing to be heated up. Okay, so that the reaction can happen over there. If we are heating everything, what will happen is the growth will happen at the walls as well. Okay, so these are the things. Now first, the precursor. Let us come on the precursor. The ideal precursor should be volatile. Volatile in the sense, it should generate some vapor pressure inside the chamber. Okay, so there are some things. If there is a precursor over here, and if we flow a nitrogen through this one, and there is a whole next line which is there, so nitrogen will be bubbled through the precursor, and it will get out through this opening to the chamber, which will carry the precursor molecules along with that, and there will be growth. The growth will happen over there. Okay, so this is kind of volatile. More is the volatile, more will be the precursor partial pressure that you can create inside the chamber. Okay, and liquid and gas at room temperature. Okay, solid is not usually preferred because there will be very less partial pressure of the solid. If solid is kind of it can sublime at some temperature. Some copper kind of precursors are there available in the market, which is in solid form, but it sublimes at some temperature. Okay, it sublimes at some temperature, and which can create a partial pressure of the we can heat it up, and we can a desired partial pressure can be created inside the chamber, and which will give us the deposition of the material over that substrate. Thermal stability, and one thing is, most of the precursors are should be thermally stable, because while transporting there is some during the transport or storage, they should not get degrade. Okay, if we are keeping at somewhere where there is some higher temperature, because from one region to another region, there is a temperature difference is always there. And if something leaks, or it should be thermally stable actually. It should not get blasted, because and it should not create that much of partial pressure inside the bubbler itself. There is a bubbler kind of thing that is there, where in which the material is there. Okay, so it is transported from other countries, so during that it should not get blasted. So a proper care is taken when these kind of precursor are transported. So they should be a bit thermally stable, so they should not get blasted. And okay, there is a like processing window. Decomposition happens, we will come in the next section, where the silicon is grown from the silicon hydroxide. So we will come. So at decomposition, there are some things. One is decomposition, one is a chemical reaction method. Okay, so we will come on that thing in the next section. So one thing is, and another thing is volatile, non-contaminating, and stable byproducts. This thing is like non-contaminating to the environment, and this is stable byproducts. After the reaction, there are byproducts which are exhausted through the out of the chamber. So they should not contaminate the environment. The byproducts should be like that. They should not contaminate the environment. And the post processing, if we do the post processing, if they are hazardous to the environment, if we do the post processing, that should be cheaper or something. Okay. And another thing, readily available, consistent, and pure and cheap. The same thing. And this should be a non-toxic and non-pyrophoric. Again, the same thing. Non-toxic. It is most of the precursors are toxic and pyrophoric as well. That one thing we will see in. Okay, one thing we will again see in ALD. In ALD, that you will get a flavor of that the toxicity and pyrophoricity, because at that point we require a highly reactive precursor. Okay, highly reactive, that can be done at lower temperatures. It should be reactive. The process can be carried out at lower temperatures. Okay. So there are various precursors available in the market, which are which you can use for the CVD and ALD processes. So silicon hydride, NH3, CH4, these kind of trimethyl aluminum. So these kind of precursors are available for deposition of silicon, nitrogen, the silicon nitride. These two precursors you can use. The carbon, if you are silicon carbide, you want to deposit silicon hydride and this methane, that you can use for the silicon carbide growth. If you want to deposit aluminum and oxide, also you can use H2O as well, along with this alumina, or ozone as well, with this aluminium to grow Al2O3. Or if you want to deposit aluminum only, you can use these kind of precursors. Okay. And there are, for most of the materials you will find the precursors. So that is why there is a very wide range of materials that you can deposit through the CVD and ALD process. Okay. And what is the mechanism? Let us see the mechanism of the CVD. So this is the reactor chamber. And in the reactor chamber there is a flow of the precursor that we are doing. We are creating a pressure difference, and there is a flow of precursor. Okay, which is along with the nitrogen or anything. Argon can be there, nitrogen can be there, and with the flow there, this is the wafer over the susceptor. The wafer is kind of a, you can say this is the working as a substrate. Okay, and with this flow there is a diffusion of the precursor molecule from this point to this point, that we will see there is a diffusion. Why there is a diffusion? Okay, that we will see in the subsequent slides, that there is a diffusion of the precursor molecules from this laminar flow, this laminar flow of the material to the wafer, and where it reacts, it get adsorbed over the substrate, and there will be a surface reaction. The reaction is happening, and there will be, after the reaction there will be some byproducts. They will get desorbed, they will diffuse out through the with the gas itself, with the carrier gas nitrogen itself. Okay, so this is the thing. And now the same thing is written over with the first is the forced flow transport of the reactants in the reaction chamber using the pressure difference. So these from point to point it is written over here. You can read. I will share the these notes. Okay, now diffusion to the surface, that there is a diffusion from this laminar flow of the gas to the wafer, to the substrate. So this, how this diffusion happens, so that we will see. Okay, so okay, when there is a laminar flow of the gas, this is the profile, velocity profile. This is the velocity profile of the gas, of the precursor. This is the substrate. These are the substrate. This is the susceptor over which there are we have our substrate or our wafer is kept. Okay, this is the velocity profile, and this, there is a boundary, there is a layer which is stagnant. Okay, what we can say is, just give me a time, I will see. Okay, and because of the this, at this layer, at this point there is a no slip condition. Because of that no slip condition, there is a layer which of the gas itself, okay, through which this cannot be so there's this layer is stagnant. Okay, stagnant is in the sense there is nothing is kind of flowing through the flowing, like kind of streamline flow is not there. Okay, in this layer this delta is the thickness of that of this layer, that stagnant, or we can say the boundary layer. Okay, this boundary layer is formed when there is a laminar flow over that over the through the pipe or through the reactor. Okay, so if you zoom out in this section, this is kind of that zoomed out section. Okay, so this is the stagnant layer, this is the stagnant layer, and through this stagnant layer there are molecules of the precursor. They will diffuse through this stagnant layer of the gas which is there. So these molecules will get diffused and will get adsorbed over that. Okay, so first we need to find out the diffusion of the gases. Okay, diffusion of the gases that is happening through this delta layer of the thickness. First we need to find out the thickness of this stagnant layer, this boundary layer, the thickness of the boundary of this layer with x. This is the direction with the length. Okay, that we need to find. So, and then there is we will find the diffusion. Okay, so the boundary layer near the substrate is, this is the profile of the boundary layer, delta x. X is the distance. Okay, so this depends on the viscosity of the gas, density of the gas, and velocity of the gas in the bulk, this velocity. Okay, so at initially near to the substrate, when it is at the initial part of the chamber, we can say initial part of the chamber, that this delta, the boundary layer thickness is lesser, and with this direction, with the x, we are going from initial part to the with the we can say distance, this stagnant layer, boundary layer thickness is increasing, we and which is captured by this formula. Okay, with x it is increasing. Okay, it depends on this one. So you can calculate the delta average thickness of this of the boundary layer. If it just suppose you have a L, this length of the reactor is L, you can just integrate it from 0 to L delta x dx. So it will come, this will be the formula for after solving the integration, you will get this one. Okay, which is equal to 2 by 3 and into L by square root of the RE. RE is nothing but this is the okay, slightly different in formula from this is the Reynolds number. Okay, RE, I think or if there will be, it will be different, I will tell you, but I think this is the Reynolds number only. That actually I didn't check that thing, this particular thing. So L is the length of the reactor. The thing you need to know is this delta is increasing with thickness, with length of the reactor. Okay, in this direction it is increasing. The so how does this boundary layer depend on the temperature and pressure? So okay, this is the viscosity. Viscosity is given by this formula, and this viscosity is kind of sublinearly dependent on the temperature. It is not that much, there is no exponential dependence of the viscosity with the temperature, and the same thing is happening with the density. Density is inversely proportional to the temperature but directly proportional to the pressure. Okay, so if this delta is dependent on the pressure, okay, it is like this. So this boundary layer thickness, if it will be pressure, okay, one thing is what I want to tell you is, okay, here, if let us suppose if the pressure is higher in this region, okay, if the pressure is higher in this region, so there will be a more flow, the velocity will be higher. Okay, velocity will be higher. If the velocity will be higher, if just intuitively think of this thing, if you should get the intuition that if the velocity is higher, this thickness will be lower at this position. Okay, because of the higher speed, this thickness will be lower. Okay, and which is due to the pressure difference. More is the pressure difference, more is the pressure, then thickness will be lesser. And the same thing is this thing. Okay, boundary layer thickness is reduces with the higher pressure, and it increases with the higher temperature because of the random motion, maybe because of the random motion. This okay, and other thing, this delta from the formula itself also, no, it is not given. Mu is there, it is mu and rho, it is dependent. So from mu it is directly okay, one thing is actually I just forgot this thing. Okay, from what you need to remember is, in this case, is a delta is is dependent on the temperature and pressure dependence. If the pressure is higher, the delta is lower because there is an inverse relation. If temperature is higher, the delta is higher in this case. Okay, and one more thing is, there is kind of no that much effect of the temperature on delta, because there is this is weakly dependent on the temperature, temperature and pressure. Okay, there are some things that we have previously seen in the Arrhenius plot of kind of thing. So where there is an exponential dependence on the temperature, that we will come in the come in subsequent slides, where our where our this deposition rate is exponentially dependent on the temperature. Okay, so there is very weak dependence. So I'll go through a bit faster because there are only 20 minutes left. So in solid state growth, there are two processes happening. One is the one thing that you have seen is the is what is oxide layer growth, oxidation, whether it is dry oxidation or let us say the dry oxidation only. So here oxygen is there in SiO2, this is Si. Okay, so oxygen goes through diffuses through SiO2 and it reacts at the interface with silicon forming SiO2. This is the same thing. There is a diffusion of the precursor through the boundary layer. Okay, this is the diffusion of the precursor through the boundary layer. This is the precursor going through the boundary layer. Okay, and this is the deposited film at the, this is the interface. Okay, where the reaction is happening at this position. Reaction is happening. Okay, at this interface reaction is happening, and the two things which there is a flow of oxygen which is determined or the precursor which is determined by the diffusion, and the another thing, this flux, second is the reaction. Okay, reaction is happening. One is the diffusion and another is reaction. So for at equilibrium, what will happen is this F1, this is the flux of the precursor, and there is a reaction kinetics is there, that reaction is also happening. So this F1 should be equal to F2 at equilibrium, because if there is excess, that won't be of no use, because if oxidation is more, if diffusion is more but reaction is much slower than the diffusion, so it much slow. Okay, reaction is that there will be kind of accumulation, but that won't happen because of the of concentration difference. Okay, that won't happen. So at this position there are flux, we have related these to the flux, so there will be F1 is equal to F2. One is related to reaction, one is related to diffusion. That you need to remember. Okay, so the growth rate will be first F1, this flux is equal to which is given by the Henry's law, that will be equal to F1 is equal to, there is a diffusion of that diffusion coefficient of the precursor into the concentration difference. Cg is the concentration of the gas at the interface, at the boundary layer interface. Okay, so concentration, and C0 is the concentration at the interface where there is a reaction is happening. Okay, Cg minus C0 into D, which is given by, and a delta del of C by dx. This is the concentration gradient. Okay, this is the concentration gradient which is directly proportional to the flux. Okay, and diffusion, this is a diffusion coefficient which is there. So flux F1 is given by D into Cg minus C0, or we can say that this diffusion concentration gradient, D multiplied by concentration gradient. Concentration gradient is because we are assuming it is a linear dependence with the thickness. Okay, that is why this is nothing but Cg minus C0. It would have gone through this profile or so, but it is linearly dependent. Okay, so this is the case. F1 is equal to, and F2 is equal to how much the concentration C0 it is consuming. Okay, how much this is consuming. At this position, at this position, the concentration of the gas or gaseous precursor is C naught. Okay, the reaction kinetics, we are assuming it is a first order kind of reaction is there. F2 is nothing but equal to K into C naught. Okay, and the growth rate dx by dt, then the growth rate dx by dt is given by Cg by N into 1 over 1 by H plus 1 by K. H is nothing but the Henry's coefficient. Henry's coefficient is equal to d by delta. Okay, d by d is the diffusion coefficient, and delta is the thickness of the boundary layer. Okay, N is the number of atoms deposited material in a unit volume. The deposited material is nothing but this substrate over the material. Okay, this is the number of atoms or which are getting deposited. Okay, because this is the rate, right? Dx is nothing but per centimeter cube, number of atoms per centimeter cube. That's why we need to divide it by the number and with the volume. If you have multiple gases, okay, multiple gases that you have seen, maybe there is a growth of silicon over silicon. Okay, that at that time you can use a single gaseous precursor. Okay, this is given by a single gaseous precursor, which is nothing but the concentration of the single gas. Cg is given by the concentration of the single gas. But if there are multiple gases, that you need to find what is the concentration of that particular gas. How will you find that? But you only know at that point there is a pressure, because in chamber what you can find is there is a pressure, but you cannot find the concentration. Okay, concentration can be anything that is going inside the chamber, because there are some SiH4 is also there, or any AlCH3 is there. AlCH3 thrice of AlCH3 is there, which is aluminum, trimethyl aluminum. If or silicon okay, amine NH3 is there. Okay, so if these things are there, how will you differentiate the concentration? Okay, but you have the pressure. So luckily we this is the given by a formula which is Dalton's law, how you can find out the partial pressure. Okay, for a particular gas, okay, the concentration is given by the pressure of the gas divided by kBT. Okay, this is the formula which is given, and for Pg is different. Pg is the partial pressure of the gas, that if there are Pg1, Pg2, Pg3, Pg4, there are several gases. Okay, so Pg is not the total pressure. Okay, Pg is not the total pressure, but it is the partial pressure of that particular gas. And from here you can calculate the total pressure is given by the if Pi is the partial pressure of each precursor, and with the summation of the Pi of the partial pressures of all the gases will give you the total pressure. Okay, from here you can calculate the this concentration. Okay, Cg by C total is given by Pg by P total is equal to Y, and okay, from here the growth rate, then the growth rate is given by P total. From here P total into Y. Okay, this by rearranging these things, if you put all these things here and rearrange them, then you will find the growth rate. Rearranging in the sense growth rate in here, if you put the Cg and N, all these things, you will find that this growth rate is given by total pressure of the inside the chamber divided by N kBT into Y. Y is dependent on the particular gas. Okay, Y is dependent on the particular gas, because this is given by the partial pressure of that particular gas into 1 over 1 by H into 1 by K. Okay, So now what you have is the growth rate is proportional to the partial pressure of that particular reactant. Okay. Now now here comes the two regimes in the sense, if okay, here what we have seen is there were two things, F1 and F2. Okay, one is F1, flux which is due to the diffusion, one F2 which is due to the reaction. Okay, these two fluxes, if they depend on the reaction and diffusion, diffusivity, F1 depends on the diffusivity of the precursor through the boundary layer, and F2 depends on the reaction rate or reaction kinetics of the precursor with the substrate. Okay, if H is very higher than K is the reaction coefficient K, and H is the Henry's constant, which is nothing but D by delta. Okay, D is the diffusion coefficient. This H depends on diffusion. Okay, if H is very higher, that means the diffusion is much faster than the consumption. Okay, consumption in the sense I am saying, consumption is in the sense I am saying at this point the reaction is happening, but it is diffusing much faster. There is no limitation of the precursor at this point. We have the plenty of precursor, but the reaction is not that much faster. This is this condition H is greater, very greater than K is saying that thing. Okay, if H is greater than, this formula reduces to this one. Okay, P total by N kBT into Y into K, and this K is the reaction coefficient, and it depends on the temperature exponential. It varies with the temperature exponential in this fashion, and at in rate limit, this is the reaction rate limited. Limitation is our reaction rate limited means our limitation is the reaction rate, not the diffusion. Okay, this is the reaction rate limited regime or reaction rate limited growth regime. Okay, and as you can see, there is an exponential dependence on the temperature, and that is why the growth is very sensitive to the temperature in this case. Okay, the another case is K is very greater than H. In this case, the reaction is much faster than the diffusion. Okay, we are limited by the diffusion because we do not have the amount of precursor at the interface where the reaction is happening. We are limited by the precursor. Okay, this is diffusion is less. Okay, in this case, so in this case it is reduced in this formula, and it is this is the case. It will reduce in this formula where D by delta. Okay, so this is mass transport limited growth. Mass transport limited growth is the same that it is limited by the diffusion. Okay, growth sensitive to gas flow dynamics of the reactor. Actually, it depends on the structure of reactor. Okay, the geometry of the reactor, it depends. Okay, what will be the growth rate of the film or the substrate? Okay, it will depend on that. Let me check how much is left. So okay, because this why the this like growth sensitive to the reaction dynamics, because this delta we will see that this delta depends on the shape of the reactor. Okay, that we will see. Okay, the growth rate effects of the pressure. Okay, so if the okay, this is the reaction rate limited, and this is the reaction mass flow limited. Okay, and growth rate directly depends on the partial pressure of them. If you increase the pressure, that will directly increase the growth rate. Okay, and one more thing, just you need to know that it is directly dependent on the pressure. Higher the partial pressure, higher will be the growth rate. That's it, that you need to remember in this case. And growth rate with the temperature. So there are two regimes that we have seen. Is one is the reaction rate limited, one is the mass transfer limited. Mass transfer limited, that is the diffusion limited. Okay, so we are assuming that H is equal to D by delta. Okay, H is D by delta is constant with the temperature. There is no, diffusion is not dependent on the temperature, because there are several types of diffusion. Okay, that here is the precursor. Okay, I'll tell you, there are several type of diffusion. One is gas molecules in solid, one is gas in liquid, and one is gas in gaseous environment. Okay, what we are looking at is gas in the gaseous environment here, and here in gaseous, that is not that much strongly dependent. This diffusion coefficient is not that much strongly dependent on the temperature. So this, and also the delta is not that much strongly, that we have seen in that previously. Where is that? Here is delta. This, okay, that you can see this delta is not that much strongly dependent on the temperature. It is very weak polynomial dependence. Okay, it is very weak polynomial dependence. So we will see. Okay, so the diffusion is constant. Diffusion term will be constant with the temperature. Okay, it is not varying. This mass flow, what to say, the diffusion limited growth is constant with the temperature. Okay, but as we have seen, the reaction rate limited is is exponentially dependent. It is Arrhenius kind of dependency is there. So it this will be will follow this one, because this is 1 by T, which is the Arrhenius kind of plot will be there in this one, which will be a linear in this one. Okay, in this kind of graph. Okay, so the net effect will be this blue line. Okay, this blue line, the net effect will be the blue line. So in this higher temperature regime, okay, in this higher temperature regime, there this is mass transfer limited. At lower temperature regimes, it is like reaction rate limited. Okay, reaction is not that much happening faster at the lower temperatures, and in this case, the reaction is happening much faster, but the diffusion is not happening that much faster, because diffusion is constant throughout the temperature. Okay, so the next thing is a uniform growth won't happen, because there will be this growth rate. Growth rate is inversely proportional to the delta. Delta is the thickness of this boundary layer. So with the length of the reactor, there the thickness increases. Therefore, so the growth rate will be decreasing with the wafers which are kept at the end of the reactor, they will have lesser deposition, and then the wafer which are in the front. Okay, the thickness will be lesser towards this end. So I'm just effect of temperature, I'm just skipping these things. So this is kind of the reactor design, that you can design your own reactor like this. You can make a wedge kind of thing. So there will be a constant boundary, constant delta. Okay, this delta, the boundary will be constant. Okay, then what we say is this boundary delta will be constant, which is given by this formula, that is mu x divided by rho into v. So we can, because there is the the area, cross sectional area of the reactor is decreasing, so there will be a fast this will be faster, and with the velocity we can tune the delta. Okay, with velocity you can tune the delta, and accordingly you can tune the tune your design such that there will be a constant delta. This boundary layer, thickness of the boundary layer will be constant. Okay, that you can see. So there are some things there is hot wall CVD, cold wall CVD, these things, that atmospheric CVD. So these things you just have a look. These are not that much typical. The typical thing is this one only, that I will show you. In low pressure CVD, what is this range of the temperature is increased. Okay, this range of the temperature is increased because at lower pressure you can increase this range. Okay, that just go through the slide, that you will get it easily. Okay, there is not that much typical thing in this one I wanted to tell, but because of the less time, so we can discuss in the next session. If you have any doubts in this section, atmospheric pressure CVD and low pressure CVD, so we can discuss in the next section. So if you have any doubts, you can ask me, or we can close today's session.
Okay. Yes. So thank you, Anil.
Okay, you have any doubt?
For this session, I will
Okay.
Reach out to you for any questions.
Yeah, sure. Anytime. Yeah. Okay. Oh, yeah.
Okay, thank you very much, Anil.
Thank you for attending this session. Yeah, thank you.
Thank you. Bye.